Okay, so welcome back to another video. So in today's video we have the following indefinite integral sine of x dx. Wait, there's no x. In fact, we have a differential dx inside as an argument for sine. Oh wow, now that's something new to bring to the table here. I'm sure many of you guys have never seen anything like this before, and I know what your first thoughts are. This is probably possible to integrate. Well, I will say that myself too. But there's actually a way to rewrite this integral, and the way to do this is we can actually rewrite this in a form of a limit, and then we can actually do some algebra from there. So as you see, what I'm going to do is I'll just define this indefinite integral. We'll call that I equals sine of dx. Now think about this. Dx is a differential, right? So when we're calculating integrals, for example, we have integrating in respect to some variable that's represented by dx. Well, in this case, in respect to x. But that's also if you think about calculating like areas with the rectangles, it's actually the distance between the subintervals. So if dx is a form of is basically like infinitesimal, so that means we're making this approach to zero, so that way the approximation of the integral is accurate. Rather, as we get closer with each, like more rectangles, in other words, then I can actually rewrite dx in a form of delta x, an infinitesimal, and then make that approach to zero. So that's hence where the limit expression comes in, which is very interesting. So then now we have that this is the integral, and then the limit as delta x approaches 0 of sine of delta x, right? Now over here, what I can do is that I can multiply and divide a delta x that's still equal to 1, so nothing's really being like changed. Really, we're just fixing the identity here of the expression. So that means we have delta x and then sine of delta x, then we divide this by delta x. Okay, now that would mean that this is with limits of products. I can actually write this as a product of two limits. So we see that this is the limit as delta x approaches 0 of sine of delta x, then divide by delta x, and then we multiply this with the limit as delta x approaches 0 of delta x. Okay, but what's really neat is that we know that the following fact for the limit. We know that the limit as x approaches 0 of sine of x over x is equal to 1. So therefore we can actually use this following fact to say that this limit over here is actually just equal to 1. So this means, now keep going from over here. So now that we have the integral, then 1 times the limit as delta x approaches 0 of delta x. Therefore, keep going forward, we have that this is the limit as delta x approaches 0 of delta x, which in other words, that's another way of defining a differential dx, and we could say that this is just the integral of dx. Of course, anybody that's taken basic calculus with integrals specifically knows that this is just the x. And then, of course, indefinite integrals, you must add your constants, so plus c. And there we have it. Yeah, that's, I bet you weren't expecting something like that. Now were you? Now, you might be thinking, what if we were to have something like, maybe, for example, what if it was cosine of the input dx? Now, would that following argument still work if we were to work this out and replace this with cosine? Well, I'll leave that to you guys to discuss. So yeah, that's pretty cool if you ask me.